All right, let's talk about the conversion of alcohols to alkyl halides using the SOCl2 and pyridine. Now, SOCl2 is called thionyl chloride. I doubt you need to memorize names or anything like that. Most instructors aren't too picky on that portion. Now, when it comes to the OH group, it's a poor leaving group. So this is the way I think about it. If you go to a party and somebody is serving alcohol, do you want to leave? Hell no. Excuse me, heck no. So what's going to happen is it's going to require more energy in order for that OH group to leave. So we're going to use this in order to convert the OH to a good leaving group. So it's bad right now because the alcohol is being served at the party. But once it gets too hectic, it starts getting bulkier, too many people arrive at the location, it's like, all right, I'm ready to leave. So that's the kind of concept that I want you to think of, okay? So let's get started. Whenever you see a problem that starts off as such with stereochemistry, you need to find the R and S notation of it. So we're gonna do that together. 1, 2, 3, that's counterclockwise. And the fourth priority is in the back, so that is S notation. Great, they normally give you points for this as well, and labeling it as the proper alcohol, which it's a secondary alcohol. So now when we think about the mechanism, bad leaving group, oxygen has lone pairs. So this is considered our nucleophile, and it's gonna attack the electrophilic sulfur center. So it's going to attack the sulfur and kick out the Cl. So this whole group acts as my electrophile, as this acts as my nucleophile, and U standing for nucleophile, okay? Now, what does our picture look like afterwards? Now, I'm doing this live so that way you can follow along carefully and see what's going on. So as soon as this oxygen, the OH, is connected to the sulfur, I move the hydrogen down, and now I'm connecting the rest of the thionyl chloride that we just had added. So it looks like this. The reason that the oxygen has a positive charge is because oxygen should only have 2 bonds, and it has 3, so review your formal charges. Now, the next part is using the pyridine, which is this structure. We're gonna use this to stabilize the oxygen. So we're going to put oxygen back to having a neutral charge, which means this will grab the hydrogen because that's acting as your new nucleophile, and then it will break the bond onto the oxygen, giving you now and I tend to put things in a lot of different colors so that way you can physically see everything that's happening. And then this, and I suggest that you also use colors when you're, just flip that around, when you're doing mechanism, because it helps you keep track. So your arrows tell a story. That's what a mechanism is. But if you're not being meticulous about how you go through a mechanism, that's what's going to give you the most problems. Now, remember we kicked out the Cl. I probably should have put it off to the side. There's that Cl minus. It's just going to travel all the way down until we need it. So now this must attack the opposite side of now what we made was a good leaving group. So all of this became a good Lg leaving group. Now, why does it have to attack? This has to attack opposite of the leaving group. Remember, these mechanisms are SN2, which means not only are they concerted, we'll get to the concerted portion in a second, but they also cause inversion, which means a flip of stereochemistry. So in order to flip something, you should attack it from the opposite side. So because this oxygen is on the front, that means the Cl is coming in from the back. And when it does, As soon as it does that, this bond, I'm gonna change colors just so you can see a little bit more. This bond here is going to collapse in between the oxygen and the sulfur to make another carbonyl, and then this Cl is going to leave. So now I'm expecting this to look like the Cl is going to be on the back, meaning the hydrogen that was once on the back will be on the front. Now this, the sulfur group, you have the sulfur that still has the carbonyl that's in pink. It still has the one bond that's in pink, and it has this oxygen that's purple that's creating that bond. So that bond that was purple is conjoining with the pink one that's there. And then you still have the Cl minus. So that's plus Cl minus, and you also have, just flipped it around a little bit, this group, which is the pyridine that had the positive charge. If you wanted to, because these two are unstable, this negative can grab this hydrogen and stabilize this as well, but that's not our main concern. Our main concern is the final answer being this structure. So this is our final. Now let's see if everything makes sense. 1, 2, 3. It's still going counterclockwise, which is normally S, but the fourth priority is in the front, so it can't be S. It's now R. So anytime we use the SOCl2, we are expecting SN2 tendencies, and we're going to get a inversion of stereochemistry when we do this mechanism.